welcome back to the Rage Racing YouTube channel. Today we're going to talk about the flow bench. The flow bench is probably my second favorite tool in the whole shop. My favorite tool would be the dyno, and I'll show you that on another day. But for right now, the flow bench. So I'm going to talk a little bit about how this works, a little bit about how to use it, and what the numbers mean that comes out of it, and how an engine builder could use those numbers to design or build an engine. So let's get started. This is a Superflow 110 model. It's actually, I believe, their smallest unit, but it works really good. It does a great job on these Harley-Davidson cylinder heads, and I've actually used it to flow automotive heads on it too. I've had even big ported Brodix small block Chevy heads on this thing, and it works just fine. Works just fine. So in general, what the flow bench does is it measures the amount of flow potential of whatever flows air. It could be a cylinder head, it could be an exhaust pipe, intake manifold, carburetor, whatever you can bolt to this thing that flows air through it. This device will measure how well it flows that air. What I have bolted to the flow bench is a cylinder and cylinder head off of a twin cam Harley-Davidson. This particular head has already got big valves installed. It's been ported, the intake's been opened up. This thing's all set to go. So this is what we're going to be testing with today. As you can see, I have a length of exhaust pipe in the exhaust section. I have a kind of a rounded adapter for the intake to allow the air to flow into the cylinder head as smoothly as possible without any sharp edges. Sometimes I will flow these with the intake manifold attached, but for right now I have this little air entry thing to make sure that there's no, I guess like turbulence or eddy currents against the sharp edge of the intake port itself. Up here I have a fixture that is measuring the how far open that the each valve is, and with a screw that allows me to open the valve itself, so I can actually twist this with this wrench here, and I can open and close the valves to whatever I want to the thousandth of an inch. So usually I'll test in 50 thousandths inch increments, starting at 50 and going all the way up to 6 or even sometimes 700 thousandths lift. So along the bottom here is one thing, it's an on-off switch to turn the unit on. There's an exhaust and intake switch. This reverses the direction of the airflow through the unit if you want to measure the intake airflow or the exhaust airflow. There's also a intake and exhaust regulator valve that opens and closes a port which allows a certain amount of air to go through the unit. On the very top of the unit is actually calibrated holes here with these plugs. So the way these work is, as you're testing, if you want to add or subtract more airflow through the whole unit, you use these calibrated holes that pass, a very specific amount of air through there. And you could use different combinations of holes to get the amount of airflow that you want. So you might do 1 and 2, 1 and 3, 1, 3, and 5. And there's a chart back here, which you might not be able to see, but there's a chart back here which converts which holes or combination of holes equates to how much airflow that the unit is, is currently flowing. Let me flip those back there. On the left here is a manometer, a liquid-filled gauge, and this measures our test depression. So the test depression is the difference in pressure between the intake side and the exhaust side of the flow bench itself. This particular unit works best at 10 inches of water. Can test from 0 to 16 is what the gauge says. Usually I try to aim right for 10 inches of water, because that's what this machine is actually calibrated for. For the test depression, 10 inches of water is literally if you had the depth of 10 inches of water, the amount of pressure that would create would be the amount of pressure difference between the intake and exhaust side of the flow bench. So for air to move, there has to be a difference in pressure from one side to the other, and that's the amount of difference there is. The center manometer reads percentage of airflow. So as I said, these holes up here can pass a certain amount of air through them that's been pre-calibrated. So the chart back here gives us whatever the maximum airflow through these ports would be up on top. And then this center manometer here gives us the percentage of whatever that maximum is. So of course the maximum would be 100%. If this meter says we're at 83%, then we know that 83% of whatever the holes up here dictate is how much actual flow is going on. For example, let's say with our, we have holes over here that say are supposed to flow, say 100 CFM of air at 100%. And as we're using our units, it's on, it's running. And when we get to, for example, 200 thousandths valve lift, and it says we're at 75% flow, that means 75% of that 100 CFM is what it's actually flowing, so 75 CFM. So that may be confusing. I'll show you a little bit about how this works, but the important thing isn't exactly the specifics of how this works, but more of the information that this thing can give us is what I'll explain later in this video. So now we have a closer view of the flow bench, and right now we're just kind of focusing on the dials here, and right now I'm just going to work on the intake port, which is the yellow dial. And I hope you can see these manometers and kind of watch how they go up and down as I do this. I'm going to test a handful of lifts. Maybe I'll start at 100 thousandths and work my way up to say 500 thousandths, and probably just go about 100 thousandths at a time. So I'll do 100, 200, 300, 400, and 500 thousandths. Just get an idea how it works. Now I know you can't see the whole flow bench. There's dials in the bottom that I'll be working, and there's these plugs on top. So if you see me reaching down here, I'm opening up the intake flow dial, and if you see my hands up here, I'm moving or plugging in ports that we saw on the top, and hopefully you can see kind of what's going on, mostly what's here, because this is where like the interesting stuff's kind of happening. Now there are a couple of other gauges on this thing. There's temperature gauges. There's a temperature gauge here, and there's a temperature gauge on the bottom. So that's because, as you know, the fans that are in the this unit, they're pretty strong, and they will heat the air as they pump it through the unit. So you have to know your intake and exhaust temperatures and keep track of that with every reading. And there's a correction factor for the temperature difference to make sure that all that is solved for in the end when you crunch all the numbers. So okay, I'm going to turn on the unit. Looks like everything's pretty much zeroed out on our gauges and everything here. Now this is going to be loud, so you're not going to hear me talk. You're just going to hear the unit turn on, and I'm just going to go through do this. So, yep, just sit back and watch. So right now we got 10 inches of water of depression, and we're reading about 85.5%. 84 CFM of a total 100%. Let's go to 300 thousandths. Now as I open up the valve, flow gets easier through the machine. The depression drops, so I can increase more air to bring the depression back up. We're also going to open up more holes. Alright, we're all open now. Air's still going to get warm at about 100 degrees. About 60%. Of the total of this unit, which is 185 CFM. 400 thousandths. Increase airflow. And finally, we're going to go to 500 thousandths. Pretty loud, isn't it? So, as you saw at the red string, there was a significant amount of air coming out of the top of this thing. So right now I got the valve at 500 thousandths lift. So it's only about half inch of lift, and we're getting all that airflow at just 10 inches of water depression. So the head's flowing really well. So that's basically how it works. It's just a real quick rundown. Next I'm going to talk about the numbers that come out of it and how those numbers are useful to us. So this is some of the information that I handwrite as I'm doing the test on the flow bench. So I'll write down things, for example, of course the valve size, the amount of area that the valve stem takes up. I also write down the test results. So every time I do a test on a cylinder head, I first put in a calibrated plate and test to make sure that I'm within the standards that should be, and apply a correction factor if I need to. So yeah, this is all the information of just the intake valve. Of course, like I said, you have to write down the temperatures of both temperature gauges, the percentage of flow, the test pressure, the lifts, all that kind of stuff. It says orifices, that's what holes on top are opened up, so we know what the total flow is supposed to be. That's the intake, this one's the exhaust. There's a lot of handwriting of information that we're getting off this flow bench. And actually, this is just straight flow. This doesn't even include putting in a device that actually measures air speed and all that kind of stuff. But I'm not going to cover that right now. This is just the general use of the flow bench itself as far as just getting airflow in and out of the cylinder head. So then after I have all my handwritten notes and I'm done testing, I actually put all that information into a spreadsheet that I made myself on the computer, and that prints everything else all nicely and calculates everything for me for the flow efficiencies, the actual total flows, all that kind of stuff, factoring in the temperature differences and all that kind of stuff. Again, this is just for the intake valve. And this is for the exhaust valve up here, and there's some extra notes and stuff like that down there. And once we have all that information, I can send it to the graph. And I can print out a graph showing exactly how that cylinder head works. So to the left here is our airflow at 10 inches of water. At the bottom is the valve lift, and then the graph curves up on top. So this particular head, as you can see, like I said before, has already been ported, big valves, all kind of stuff installed. And you can see the difference between ported intake from top to bottom. You got in blue the ported intake. In green is the, let's see here, stock intake. In red is the ported exhaust, and black is the stock exhaust. And you can see how the ported figures are much bigger than the stock, which would make sense because this head's been modified pretty extensively. Okay, so now we have all this data. What do we do with it? Well, there's a few things we can do with it. For one thing, of course, I test heads stock before I modify them, and then I test them again after I modify them, and I can tell what, for example, percentage of improvement that I've made. Hopefully there's improvement. I've actually seen plenty of cylinder heads that have flowed less than stock after they've been supposedly ported. It's an easy trap to take material from the wrong areas, to do the valve job wrong. It's a pretty tricky thing to do correctly, and it's very easy to actually decrease flow even though your port is technically bigger. I've actually done it myself. The very first set of heads I've ever ported was in 1994 or 1995, and they turned out great. I had someone who was experienced teach me the correct way to do it, and I did it the way they said, and I put those heads on a car. It was a 350 Chevy, and that the car ran great. Later on, I decided, well, I can do better. So I pull the heads off and I completely hog out those ports, making them just huge. I pull the bowl size all the way out to pretty much the diameter of the valve. I made them, I took way too much material out. They looked awesome. Just to look at these heads, you would think they could, flow a mountain of air. It'd be ready for professional drag racing. Put them back on the car, and the car slowed down significantly. Those heads are junk. They used to be good, and I junked them. Took out too much material and from the wrong areas. So the flow was all wrong. Probably the velocities were down. It was just garbage. But that's how we learned, and that was a long time ago. So now I've learned my lesson. I got the flow bench now and a lot of experience under my belt, and I can actually do the right thing for porting these heads up. But that's how you learn. Sometimes you got to screw up. So I'll take the information from the flow bench, and if I've made an improvement, I can tell about how much percentage of improvement in flow I've made, and that gives us an idea as far as how much potential power you should be able to get out of the new cylinder heads. And it usually goes about 1 to 1. If you get 10% more flow out of the head, there's usually potential for 10% more horsepower too, if you take advantages of that flow, with things like compression, camshaft, exhaust, that sort of thing. But let's say you're building a new engine and you kind of want to have an idea as, well, how much power do you start with, or what kind of cylinder head should I start with if I'm aiming for so much power? Well, there's actually formulas for that, and you know how much I like math, so we're going to start doing some math. So there's a formula. So horsepower is as easy as taking 0.43 times your CFM at your peak valve lift. So 0.43 times the CFM at 10 inches of water test depression. And that gives us our horsepower. Okay, let's erase this at peak valve lift here, because now we understand that that's the flow at the peak valve lift. If the valve is not opening to the flow of the head, then, well, what's the point? So, okay, and I should also note that this is per cylinder, so you're going to take our result times the number of cylinders of the engine, and that'll give us the total. So let's say we have 0.43 times, let's say we have a cylinder head that at 650 thousandths lift flows 175 let's put it over here. CFM. 10 inches of water. I'm going to get back to that. So 0.43 times 175 comes out to be 75.25 horsepower per cylinder. So let's say you have a 8-cylinder engine times 8 makes, put an equal sign in there, is 602 potential horsepower. So that means if the camshaft, intake, carburetor, exhaust, compression is all optimized for that engine, there's a potential for making 602 horsepower out of a V8 that has 175 CFM at peak valve lift. So, and again, that's at that 10 inches of water. Not all flow benches use the same depression. You could have flow benches that flow at 23 inches of water, some at 25. The bigger ones flow at 28 inches of water. So more depression, which means more difference between the intake and exhaust on the flow bench, means that there's going to be more airflow as a result, even for the same valve lift and that sort of thing. So most of your magazine articles, most of the things you see with aftermarket cylinder heads, they're going to print the 28 inches of water number. So we'll put 28 up here. Well, there's a conversion factor to switch between the 10 inches of water to the 28 inches of water, and it's 1.67. 1.67. So if you have flow at 10 inches of water, you just multiply that number by 1.67, and that'll give you what the flow would be at a 28 inch of water depression on a bigger flow bench. But otherwise, everything comes out exactly the same. So with our formula, we don't use 0.43 anymore. If you're testing at 28 inches of water, the number is actually 0.257. 0.257. So let's just put our same situation to show that this works. So let's say we had 175 CFM before, times 1.67. The new flow is going to be 292.25. 292.25 CFM. So let's figure that out. So we got 0.257 times 292.25 equals 75.108, it kind of goes on, times 8 cylinders is 601 horsepower. So off by 1 horsepower, and that's probably just from rounding errors. So you see that the formula works both ways between 10 inches of water depression or the 28 inches of water of depression. So like just have to remember that conversion factor of 1.67. So as a quick note, you might be wondering, well, why use the difference between different flow benches? Well, I got a smaller, weaker flow bench that flows 10 inches of water, and that's what it's calibrated for. Bigger flow benches flow at 28. The 28 is, I guess, closer to what the actual running conditions of a real engine would be. It's a little bit more accurate. Those flow benches are a lot more expensive. But is there a difference in airflow and testing? So, not really. The larger flow benches at 28 inches of water are going to be a little bit more accurate. But to tell you the truth, I've used this conversion factor between cylinder heads that have been flowed at 28 inches of water and flowed on my bench that flows at 10 inches of water using this conversion factor, and I've come within 2 or 3 CFM of their numbers. Now, if you watched my last racing physics video, you know that you need to burn as much fuel as possible, as quickly as possible, to make horsepower to the ground. So to burn that fuel, you need oxygen, and oxygen comes in the air that we pump in and out of our engines. So I listed a few ways that you could increase the amount of air going in and out of an engine. I listed just making the engine bigger, more displacement, can pump more air automatically. I listed turbocharging or supercharging. I listed, of course, adding nitrous oxide, which just adds oxygen to your engine anyways, so you can add more fuel and make more power. I also said you can spin the engine faster using more RPM. Now there's another one I left out, and I'll get back to that in just a second, but right now we're going to talk about the RPM. So we know from our flow bench how much air can go through a cylinder head to give us potential power. But you have to spin the engine to a certain amount of RPM to pass that much air through it to make that power. So you notice that horsepower figure from the last formula that I gave you did not mention displacement at all. Displacement has nothing to do with that formula. Like I said, these aren't exact sciences, but it does get you pretty close. That's because the displacement of the engine doesn't have that much effect on horsepower. I know you're going to write a bunch of hate in the comments below. That's fine. I'm expecting it. Like I said, it just comes down to the airflow. So this formula I have here tells us at what RPM the peak horsepower is going to come in at. So still using our CFM at going back to our 10 inches of water figure for the flow bench that I have here. You take 2,000 divided by the cubic inches of displacement of one cylinder, and you multiply that by the CFM, again at the maximum valve lift. So right now we're just going to put in for CFM at 10 inches of water. And that equals the RPM that peak power should occur, again, in an optimized race engine. So let's put this formula to the test. Let's say we have a 400 cubic inch V8. So take 400 divided by 8, so that's 50 cubic inches per cylinder. So take 2,000 divided by our 50, multiply that number by 175 for 175 CFM, and that equals 7,000. So a 400-inch engine using the cylinder head that flows that much should make 602 horsepower at 7,000 RPM. So what would happen if we had a smaller engine? Let's figure that out. Let's take, instead of 400 cubic inches, let's take a real small, say 327. So 327 divided by 8 equals, let's take 327 divided by 8 equals 40.875 cubic inches per cylinder. Multiply it, so we take 2,000 divided by that number, 40.875 times 175. A 327 Chevy makes 602 horsepower at 8,562 RPM. So same horsepower, just vastly higher RPM, because it takes the 327, that kind of RPM, to flow as much air as a 400-inch engine would at 7,000 RPM. But it all comes down to the amount of air that you can pass through the engine so you can burn the fuel. So some people think that this formula maybe it reads too high of an RPM number. That's fine, because I've seen other numbers that would have been 1,925. Then we use the formula like that, which we can try. So we'll take 1925, divide by our 40.875 times our 175, and maybe that comes out with a little bit more reasonable, 8,242 RPM. So you're still spinning the engines pretty high to make the 602 horsepower. So what happens if we do like a breakdown? And we'll use this 1925 figure for the next calculations. Let's do a breakdown of each engine for 400 inch down to like a 302 Chevy, and just watch how the RPMs go up. Okay, here's various Chevy displacements, working with that same cylinder head, using that same formula. So for the formula this time I use the 1925 number instead of the 2000 number, kind of bring the RPMs down a little bit, but don't focus on that, just kind of focus on what's happening here. So the RPM of peak horsepower for the 400 is going to come in at 6,737 RPM to make that same 602 horsepower. That 350 can still make 602 horsepower with those cylinder heads, but at 7,700 RPM. A 327 can still make that same 602 horsepower, but at 8,242 RPM. And a 302 Chevy can make that same 602 horsepower at 8,924 RPM. So what I want you to get from this isn't the exact numbers or even the formula. I just want you to understand in your head that the most important thing is actually passing air and fuel through your engine to burn the fuel to make the power. You can spin the engine real high RPM to get that kind of power, or you can have a bigger engine that makes that same power at lower RPM and more torque. What I've kind of been showing you is last couple of videos is the displacement of the engine is, although very important, more important is the actual airflow you push through the engine. No matter how you do that, it comes down to the air going through your engine, which actually makes the power. Now, of course, these small engines spinning super high RPM, it's difficult to do that. Usually to get that kind of airflow through a smaller engine, you have to have amazing ports and flow work and all kind of stuff, because usually the cylinder bores are smaller, which means the valves are usually smaller. So it takes more work to get that kind of air through an engine. On top of that is just the sheer RPM can tear an engine apart. So if you're going to spin a lot of RPM, 9,000, 10,000 RPM out of an engine, especially when we're talking about a Chevy V8 or anything like that, you better have amazing components in there, top of the line race stuff in your engine to be able to spin that kind of RPM. The valve train to spin those kind of RPMs has to be just spot on and again of amazing quality. And that's where the bigger displacement engine kind of has the advantage, is it can make those same horsepower numbers at a lower RPM, which means you don't have to build the bottom end up near as, I guess, is extravagant, and your valve train isn't going to be beat up anywhere near amount. But at least you know that this kind of how the physics of it works. So if you wanted to do a small RPM engine that made amazing horsepower, you can do it. So why am I telling you all this stuff? So these formulas, I hope they can be helpful. They're more for just playing around and get you an idea for engine design, that sort of thing. Like I said, none of these are absolute concrete. There's so many variables, you can't break things down to a simple formula. And I also can't break down every possible aspect of an engine in 15, 20, or even 30-minute videos. So if it seems like I left stuff out, there might be either a reason or it just wasn't as important to make it into that particular video, or something I'm going to cover in a future video. So the main reason why I'm doing this and giving these math formulas and showing you what I got going on here is because I want you to kind of think of the engine in a different way that maybe you thought of it before. Just to kind of educate you on how the internal components work, how the horsepower is actually made versus what you read in a magazine or see on the internet. I want to give you a deep dive into the real aspects of how an engine works. And I plan to use this channel and these videos to go through and not only analyze the numbers and the actual physics of what's happening inside an engine, going from the very, very, very basics of someone who knows nothing about an engine, all the way down into the very, very deep science of race engines, as far as at least I can go. And if we need to go further, then I'll have other people on the channel to hopefully explain things to me and you together. So, of course, I got the flow bench here. I have a dyno that I use. It's a chassis dyno for Harley-Davidsons, and I plan to show back-to-back tests between components to test some of my theories, and this to test different aftermarket components and some of the aftermarket sales pitches that are out there to see what stands up and what's actually just junk. I have, beyond the Harley-Davidson realm, I do have a background in automotive racing. So I plan to build a couple automotive engines, and we'll go step by step through those engines and hopefully get engines actually on the track and show real life performance. So let me show you around a little bit about what some of our future projects on this channel might be. Okay, on this shelf here, you're just going to see a lot of boxes and bits and pieces of a Harley-Davidson engine. There's a cylinder head, and there's some cases, and there's a whole bunch of boxes and such. This is going to be a kind of a real hot street engine for a twin cam Harley I'm going to build for the channel. And we're going to go through step by step the performance parts I've picked, why I've picked them, and the actual build procedure. And then we'll go through the tuning, dyno tuning, and hopefully on-track testing with that engine. I think that'll be a lot of fun. And this project's just for fun. Nothing serious about this. A lot of this is just made out of even spare parts that I've had sitting around. So that'll be a fun one. Also, getting a little bit more serious is parts for a small block Chevy. You can see some Brodix aluminum heads. Those have been ported somewhat. I think I'm going to go in and port those even a little bit more, flow them and test them, and I'll put that on the channel. Of course, we've got dual quad tunnel ram. There's a crankshaft in that box, rods, valve train components, all kind of stuff. That's going to be a real fun one. So this is going to be a 388-inch stroker motor, small block Chevy, and I'm looking for, I'd like to see a minimum of 600 horsepower out of that, naturally aspirated. So that'll be a fun engine. I got some more parts up there for that, up here, so I'm pretty much all ready to go with a couple of projects I can put on this channel. Now, I'm also going to have a couple other things on the channel. Big block Chevys. And right here I'm going to show a couple snapshots of some big block stuff I have just kind of sitting around I could use. And when we're ready to get very serious, I have something that's going to be a little bit more up to speed, per se, for the serious racer or someone who wants to seriously know the real in-depth way to make a lot of power. And here you can see what I plan to use for that. Well, I'm sorry this video is a lot longer now than I was expecting. Hopefully you made it through this far. If you did, thank you. Thank you for watching. I plan to do these engine builds. I plan to go through more physics of racing. Not only the engines, I plan to go through transmissions, rear ends, tire technology, suspension technology, launching, the physics of launching off of a drag strip, physics of what happens to a car during lateral acceleration, which is turning corners. And I plan to go through all this stuff. I also plan on having guests on as far as doing interviews with local racers, shop engine builders, even suppliers and manufacturers. So I want to have this a big, well-rounded channel that's going to be useful to a wide audience, and it's going to really get down into the nitty-gritty of the physics of racing. Thank you for watching.